Hello, I'm Dr. Raymer, and today we're going to talk about growth and maturation. So, development is an inclusive term. So, of these three terms, development, growth, and maturation, development is the most inclusive. If we define development as progressive change in size, shape, and function over the lifespan, then we can define growth and maturation separately from that as growth being an increase in size over a given period, and maturation being progression toward the adult mature state. So, of course, we know that growth then is quantitative and structural, while maturation is more qualitative. Of these two, both are indicators of development, but growth, because it's quantitative, is much easier to measure. So you'll see a lot of the metrics we talk about today are metrics of growth rather than maturation. So why do we study and measure growth and maturation? Well, at the population level, data on growth and to a less extent maturation helps us understand predictable processes and create a standard time course of events. In individuals, tracking, particularly of growth, provides an indicator for us that development is either proceeding normally or deviating from what's considered normal. In addition, in the context of motor development specifically, growth and maturation create constraints, and these constraints shape motor development. So what are constraints on motor development? Well, constraints are factors that limit, contain, or as we just said, shape motor development. We talked about the mountain model of motor development previously. This is another sort of model of motor development that overlaps and interacts with the mountain model. If we think of the mountain model as being really relevant to experience, the constraints model of development focuses on constraints and divides these constraints into sort of three categories. Constraints to do with an individual, constraints to do with an environment, and constraints to do with a task, a motor task. And we'll look at an example of these in a second. The important part of the constraint model is that constraints around an individual in terms of motor development can be modifiable or not. So to understand the constraints model, let's look at a specific example. In this article, they're looking at constraints on performing a dance leap. Now here's our dancer over here, and the task constraint is how does this task need to be performed? Right? What are the criteria for success? And you can see the dancer, and I'm not a dancer, but in this task, her legs are parallel to the floor. That might be the threshold in a full split to performing this task successfully. Environmental constraints, here they're looking at a physical environmental constraint. They happen to be focused on the floor of the dance studio. So is it a spring floor or not? The environment can also include things like the psychosocial environment. Do you have a good dance teacher? Do you have people to train with? Do you have an opportunity for feedback? Those are environmental constraints. And when it comes to individual constraints, that's really what we're talking about in terms of growth and maturation, is the individual part of this constraint equation. And you can see that some of the individual constraints are modifiable. So as you train, your strength and your control is likely to change. Other constraints are non-modifiable. Your height is your height. Your body proportions, do you have long legs or short legs, the width of your bony pelvis, etc. Those things are non-modifiable constraints. And you can see there's a whole category here called Anthropometry. And these are indices for measuring growth. So let's talk about those. So anthropometry is the study of physical characteristics of the body, such as size and shape. And anthropometric measurements, the defining criteria for those is that they are both non-invasive and quantitative. So the three big ones that we're going to talk about are height and weight, and calculated from those, body mass index, or BMI. And another important one we will pay less attention to, really important in infants, for example, is head circumference. Now, one way anthropometric measurements are used is in routine growth monitoring. This is just routine collection of measurements to track individual growth. The World Health Organization, this That Who, not the great Canadian rock band, defines objectives of growth monitoring. And number one is to provide a tool for evaluating health and nutrition. Number two, to initiate effective action in response to abnormal growth. But 3 and 4 are also really important. So here, point 3 is to teach parents and caregivers and educate them about how nutrition and physical activity and illness and other things can affect growth. And the last point here is interesting. So one of the reasons to track growth is to just provide regular contact with healthcare. And yes, so you can see it's important that we have an opportunity to intervene if there's a problem, and routine growth tracking will tell us that. But these bigger sort of reasons to track growth, to create opportunities for education and additional contact with healthcare, those are really important ways to change health at the population level, just by simple growth tracking. Now, the World Health Organization also defines requirements for growth monitoring, and these really involve accurate measurements, using validated growth charts, interpreting a pattern of growth correctly, and in the case of children, discussing the child's growth pattern with the child if they're old enough, but certainly with parents and caregivers. So, little ones, before a child can stand without assistance, we measure total body length, also called recumbent length. And we do this while the child is supine or laying on their back. You can do this with a slide ruler, which is sort of the most accurate way to do it. That's what's shown in this image. It's also frequently just done with a tape measure. And you measure the distance between the soles of the feet and the vertex. The vertex is the highest point of the skull. Record the measurement to the nearest millimeter. And even though we're living and working in Canada, you need to be able to convert really readily between millimeters and inches. And kilograms and pounds when you're tracking growth. When a child can stand without assistance, we can measure standing height or stature. So the other word for standing height, stature. And that's just the distance between the vertex and the floor. You want to get the child barefoot, again. And here on the scale, this is a clinical scale. Many of you have probably seen a triangular headboard is used to create a right angle between the scale and the vertex of the skull. Now, there's situations when we can't perform standard measurements of stature. In people who cannot stand is the most obvious case. Also, people who have pronounced spinal curvature will not have accurate stature measurements. And in these instances, segmental measurements of the body can be used to estimate stature. And so all kinds of segments of the body have been used for this purpose as a proxy for stature. Biaxillary length, for example, the distance between the armpits, thigh length, forearm length, hand length. Of all of these, knee height has been identified as the most reliable surrogate for stature measurements. So knee height can be measured in a seated, on the left, or a supine position. And in each case, the knee should be bent at 90 degrees. And here are the equations for taking the dotted line measurement of knee height between the top of the thigh and the bottom of the foot and converting that to stature. Now, once you have your stature measurement, you're going to use a growth chart to compare an individual's measurement to growth at the population level. And there's at least 2 ways that growth and other measurements are represented graphically. So the first is this is the most common. This is a distance curve, and it plots cumulative growth over time. So these are American data. This is a typical distance curve for stature based on the National Center for Health Statistics data. You can see we've got stature in inches plotted along the y-axis, and that's plotted against age in years on the x-axis. You can see that this starts after birth, so it looks just starting just before 2 years of age here. So this is a stature curve, not a length curve. And you can see there's solid line for males and the dashed line for individuals identified as female at birth. Now, the distance curve shows you a few things just about sort of the pattern of growth. You can see growth cumulatively increasing from the start of the curve until the age that adult height is reached. And we can see a relatively stable period of growth, sort of between 30 and 40. It really levels out in most people. And then somewhere around age 40, we start to shrink. How depressing. So our growth starts to, stature moves in the downward direction. And it doesn't change dramatically. It's sort of half an inch per decade or something like that in most people. And this sort of shrinkage, growth in reverse, loss of stature, is due to things like compression of intervertebral discs and loss of cartilage. Now, in contrast to a distance curve, a velocity curve plots increments of change in stature per unit time. And so here you can see the x-axis, this time the height gain shown in centimeters, and it's per year. And that's plotted against age in years. The dashed line, females, black line, males. When you look at a velocity curve, it's useful for identifying periods of fast and slow growth. So what's interesting is this, we all know we're growing in childhood, but the rate of growth is actually getting slower and slower and slower. And that reverses at puberty for the adolescent growth spurt. You'll see a statistic or a measurement called peak height velocity, or PHV, and that's right in the peak of that adolescent growth spurt. So it's about age 11 to 12 for girls and 13 to 15 on average for boys. Now, in combination with stature, body weight is the most important metric of growth, and most of us are familiar with the tool we use to measure weight, which is the electronic digital scale. So this can be a standard scale like many of us have in the bathroom, or a platform scale like this little baby's on, or an alternative type of scale for people who have trouble standing like the chair scale shown here on the right. When you weigh someone, shoes and as much clothing as possible should be removed. If you weigh a clothed adult, you can deduct 1 pound. Now, early in the postnatal period, infant weight is monitored really closely, and this is to see if baby's nutritional intake is adequate. In the first week of life, it's normal for infants to lose weight, so they can lose sort of, by most standards, certainly 5% of their body weight. And this is due to water loss rather than sort of body fat loss. However, it is a sign. So early weight loss in that first week, exceeding 5 to 10%, is an indicator that nutrition may be inadequate. Maybe breastfeeding isn't going particularly well, or for some other reason, the baby's not getting enough caloric intake. Some sources will say it's lower than 10%. So some sources will put that sort of warning sign at the 7% number. Obviously, these are averages, but here's some average milestones for what happens to baby's weight. Typically, babies return to birth weight by about 10 days to 2 weeks after birth. They double their birth weight by about 6 months after birth, and then triple it about 1 year after birth. So these are just some sort of standard metrics that people can use as very general indicators. Now, as with stature, changes in weight can be illustrated using both distance and velocity curves. So here's a distance. Remember, distance curves are cumulative over life. So the distance curve is showing weight at any age. Now, typical distance curve, this is typical for weight, again, based on statistical data. And we've got average weight in pounds plotted against age in years. What you can see from this graph, hopefully, maybe, is how much weight is actually gained in adolescence. And it's a lot. So it's about 45 pounds in males and 35 pounds in females. So adolescence is normal part of adolescence is weight gain. Now, body mass index combines weight and height as just a really simple metric of body size. And it's very simple. You get BMI by dividing body weight in kilograms by the square of the height in meters. So that's the formula for calculating BMI. So to see how this works, let's do a quick example. We'll take Mary. Mary's a 46-year-old woman who weighs 132 pounds, and she's 65 inches tall. So what is Mary's calculated BMI? So the first step is convert pounds to kilograms by dividing pounds by 2.2. And again, yes, we're in Canada, but we have big neighbors to the south who often measure weight in pounds. And as a result, somehow conventionally, weirdly, we often measure weight in pounds and height too, despite our otherwise commitment to the metric system. Anyway, so divide pounds by 2.2 to get to kilograms. Convert height in inches to height in meters by multiplying inches by 0.0254. So we get her height in meters, and then we solve the BMI equation. So it's just her weight over her height squared. As a result, that puts her BMI at 22 kilograms per meter squared. And you can usually round to the nearest tenth, so we'll say it's 22.1. So how do we interpret BMI? Well, we interpret it in these fixed ranges, and they're typically, getting a little bit better at this, but typically not separated for anything, not age and not sex, and no other variable. So this is a simple depiction of the BMI scale, and I've chosen this one for a specific reason, because it uses these terms under fat and over fat, which are in fact total misnomers when it comes to the BMI. But this is how the ranges are typically split up. So a BMI of less than 18.5 is low. It's abnormally low. A healthy BMI is in the 18.5 to 25 range, which is where we pegged Mary at. And so Mary has a healthy BMI. The words over fat, so overweight, is a BMI in the range of 25 to 30, and obese is a BMI of anything over 30. Now, there are subdivisions and subclassifications of obesity on the BMI, but this number is really what the BMI was designed for. It was designed as higher than 30 is an indicator of risk for cardiovascular and other types of disease. So BMI is a useful, simple screening tool. And a BMI over 30 is predictive for future health risks, so including CVD, that's cardiovascular disease, diabetes, hypertension, certain cancers. However, the really important point about BMI is that it does not measure body composition. So BMI does not measure percentage of body fat. And I'll go back to that slide for a moment. So that's why the slide is, the scale is not great. Right? Because that's not what it's measuring. There's no indicator on the BMI of body composition. So that creates some limitations for the BMI. It's inherently limited because its ranges are not age or sex specific. Typically, they are starting to improve that. The BMI does not apply to any outliers. So it's a useful screening tool for average individuals, but not for outliers in any sense of the word. So individuals who are very short or very tall, pregnant or lactating women, and many athletes, as well as other sort of individual outliers, BMI doesn't really apply to them. There are many Olympic athletes who have BMIs that suggest that they're overweight or obese, when in fact they're in great physical health. And so it just does not measure body composition, does not differentiate between fat and muscle. It also doesn't capture body fat distribution. So it doesn't tell us where on the body the fat's been deposited. We know that abdominal body fat represents the greatest health risk and a much higher health risk than subcutaneous fat in other places on the body, but the BMI doesn't differentiate between those two. So given those limitations, why do we still use BMI? Well, we use it because it's simple. A better way to measure abdominal body fat are measurements like waist circumference or waist circumference put in ratio with hip circumference, some ratio tools to look at size of the body. Those measurements are actually harder to collect, whereas most of us can calculate BMI really readily. And that's why we still continue to use it as a screening tool. It's just important not to over-interpret it. Now, to determine whether growth is typical, measurements for individuals are compared to normative growth charts. And the way these charts first are developed, they're developed based on statistical analysis of growth averaged over large cohorts of individuals. That's the first important thing. And the second thing is that most normative growth charts use percentiles. So the percentile is a percentage of measurements in a population of typical individuals that fall below that number. Here, you can see it plotted against a normal distribution. This is where the 10th percentile would fall. So the 10th percentile is here. 10% of the measurements in a population fall below that. If a child is tracking on the 10th percentile on a growth chart, as we'll see what that looks like, it means that of 100 typical children, sort of typical statistical average children, 90% of children at that age would be taller than that child, and 10% of children at that age would be shorter. So this is a growth chart from the United Kingdom. So it's the UK World Health Organization for growth chart. This is a chart for weight in girls aged 0 to 1 years. And so you have to look first, have I got the right chart? Have I got the chart for an individual identified as female who's between 0 and 1 in this case? You can see that the chart is set up along these percentiles. So these are the percentiles, and I'll put my pen on the 75th percentile. And so this is the growth curve for children falling in the 75th percentile. Now, it doesn't really matter where children fall on this curve, right? They can be in the 99th percentile or the 0.4th percentile. So that's not super interesting. We would describe those children as being a low centile or high centile. They can even be above the 99th percentile, as this measurement is right there. That's not that important, right? So individual measurements, is a child measuring high or low, not that interesting. That's of course determined by all kinds of things. Is it a genetic influence on size, a nutritional influence on human size, etc. So there's all kinds of reasons for children to be relatively big or relatively small. So individual measurements aren't that interesting. What is interesting is tracking over time and seeing how a child's height and weight change over time. If two measurements fall along the same curve, that's kind of what we expect for that child. Here it's described as centile tracking. We could also describe it as a child's growth is following the curve. What we want to watch out for is big changes moving up, crossing multiple centiles, this centile crossing up, or centile crossing down. And if you see a child sort of, especially early in life, they're following any curve, and then they fall off a curve and start to measure way below it, that is much more of an indicator that there's something going wrong. Now, here's the link at the top of the slide to the charts that we use most commonly in Canada. So the Set2 resources from the Dietitians of Canada. And I'll just click on it for a second, point out a couple of things. So here are the resources. There's Set2. These are the percentiles that Set2 uses. And you can see that in babies birth to 24 months, this is what the charts normally look like. And you can see the length of the baby and weight are really important metrics. If you go back to a little bit older, looking at kids 2 to 19 years old, there's actually an interesting recommendation, which is that the World Health Organization now recommends BMI as the best measure after age 10 due to the variable age of puberty. And so recommends not tracking weight alone anymore after age 10. So that's a relatively new recommendation. Now, another relatively new recommendation or development is what happens when you go into the BMI calculator for kids, and you get redirected to this child and teen BMI calculator. So this is a new development, and they actually are changing the BMI slightly for people aged 2 to 19. And so they've actually created an age differentiation to account for the fact that kids are still growing and growing differently, at different velocity at different ages. And so that is both the presentation of these data and the calculation of the BMI is subtly different. Now, coming back to this idea of constraints, stature and weight, as well as other factors like proportions, place constraints on motor development. And we talked about this in the context of this dance leap. We mentioned that growth-related constraints can be both modifiable and non-modifiable. And so some things you're just stuck with. It is what it is. You might have shorter legs relative to stature, or you might have longer legs. So shorter legs, for example, influences balance by lowering the center of gravity. Longer legs influence running and walking speed. In most studies, longer legs are related to faster running speeds. Body weight also influences athletic performance, other types of movement. In some sports, increased weight is an advantage. Right? Think about sports like football and rugby. Increased weight is also good for propelling objects, things like shot put and javelin. Reduced weight is an advantage when the body is being propelled or supported. So think about things like long distance running and cycling. You want to have less body weight to move. Now, some of the most dramatic examples of constraints or how structure permits or promotes function are in elite athletes. And so we often look at exceptional athletes to see how their body structure has rendered them particularly well suited for a specific sport. So these are just some little schematics. These are actually from the 2016 Olympic Games. And the first really common example of this is Michael Phelps. So Michael Phelps has an 80-inch wingspan. That means fingertip to fingertip. He has really long arms, even relative to his height. So he's a tall person, but exceptionally long arms. And that is a biomechanical advantage for some swim strokes. Similarly, Simone Biles, standing at 4'8", is very short. So she has a really high strength to weight ratio, in part because of her height, obviously also because of her training. But her shorter arms and legs also help her perform rotations. And so that's another sort of structural advantage that Biles has. Chris Froome, 6'1" and 147 pounds. After he became a pro cyclist, he actually lost 20 pounds. So this is a huge advantage for him in terms of cycling efficiency. He also has sort of one of the highest measured VO2 maxes. That means he can use oxygen really efficiently. And so both his weight, in the case of Chris Froome, this is interesting because his height is obviously a non-modifiable constraint. It is what it is, but his weight loss, and at least to some extent his VO2 max, represent modifiable constraints. Right? Similarly for Simone Biles, she obviously trained to achieve her strength and her flexibility. Can't see red on pink there, but get the point. And so there's a blend of modifiable and non-modifiable constraints. And the last, Meb Keflezighi, who's an American, now retired American long-distance runner, he's quite small, so 5'5" and 126 pounds. So it's a lot easier for him to propel himself off the ground with that light body. He also has relatively long legs and a short torso, so his proportions represent constraints that confer an advantage when it comes to running. Now, while some anthropometric parameters influence performance in some sports, the evidence for this is far from clear-cut. We cited these extreme examples. There's a huge field of study dedicated to identifying biological variables that can predict potential or performance in sport. And there's multiple reasons for this, including talent identification or scouting, and shaping training programs. And those processes have advantages and disadvantages for youth in sports, which we'll get into later in the course. But most of us are not Olympic athletes. So there's really two important factors for most people. Many of the most important performance predictors are modifiable. So we talked about body weight as a modifiable performance predictor. VO2 max is another modifiable performance predictor. In many studies, functional tests are better predictors than anthropometric measurements. So it must be much more important in terms of your potential to play volleyball, how high your vertical jump is, rather than how long your arms are relative to your torso. So you're not necessarily, it's just really important to know, we're not necessarily limited by the body we have. One common transient constraint in motor development is associated with the adolescent growth spurt, and this is described as adolescent awkwardness. So adolescent awkwardness is a temporary disruption in motor performance, and it's associated with the period of peak height velocity, so that rapid growth phase, or PHV. Now, this isn't a universal phenomenon, and it's actually more prevalent in males. So you may have experienced this as an adolescent, maybe not. There's multiple sort of hypothesized causes for this. So one is that bone growth in length exceeds muscle development and lengthening. And so the muscles basically can't keep up with the bones in terms of when long bones are growing so rapidly. And this results in reduced strength in some movements and reduced flexibility in others. So this isn't a social adolescent awkwardness, which also exists. This is a physical adolescent awkwardness. Now, we've talked almost exclusively about growth because really that's what we typically measure. But maturation also impacts motor and, in fact, all domains of development. Now, an important definition here, when we assess development, we use chronological age as a proxy for developmental age, and they're not the same thing. So chronological age is time since birth, that's when you get to eat cake. Your developmental age reflects level of function across developmental domains. So developmental age sounds like meeting all the milestones of a typical 4-year-old. So just differentiating between those two. We know how to measure physical growth. We can do it with height and weight relatively easily. Determining physical maturation, what stage of physical development a child is at on their journey to becoming an adult, is more challenging. And so we can do this on X-ray with skeletal age. In females, we can look at the timing of menarche or the onset of menstruation. And in both males and females, we can look at the maturation of reproductive organs, including external genitalia. You can see pretty quickly that all of these are much more difficult to measure than height and weight. So if we're going to make a really general statement, it's that more physically mature individuals perform most motor tasks more proficiently than their less mature counterparts. An interesting sort of exception to this might be adolescent females. So in adolescent females, participation in sport can be associated with delayed menarche, and this may be sport specific. But data on physical maturity and stage of development is tough to get for reasons that we've already specified. It's just hard to measure these things. And the other really important consideration is that physical maturation is related to motor performance, but so is maturation in all other domains. So you really have to consider all aspects of maturity and developmental age, not only physical maturity and motor domains. You know this instinctively if you've ever worked with or coached children. You know that things like their attention span is really important, their ability to learn a motor task. And so just something to remember when we talk about maturation and developmental age, even if we're talking about motor performance, we have to think more broadly about all the developmental domains.